All right. Vinayak, I think, yeah, we are live on YouTube. So I will give you an access to kickstart the session. Yeah. Over to you, Vinayak, to get the introduction and started with the program.
Yeah, thank you. Hello, am I audible?
Yeah, you're audible. Go ahead.
Yeah, thank you. Good evening, everyone. Thanks for joining in. We got a few much trouble to complete the session on last Wednesday. So here we are. Today is the rescheduled third day session. Without much ado, let's get started. Arvind, Abhinav.
Yes, yes, Vinayak.
Thank you.
Yeah, okay. So good evening, everyone, and welcome to this third day on the bootcamp on cell chemistries, reactions, and cell testing. So the so welcome to this third day session on cell testing and characterization, right? So this is day 3 of the bootcamp. And in the first day, we had covered on cell chemistries and reactions. And in the second day, we had covered some basic calculations and parameters and understanding how some of the parameters are estimated. Right. So, and in this session, we will be looking at what is cell testing and what are the different cell testing that is, what are the different cell testing and procedures that is being performed in order to understand the behavior of batteries and cells. Right. And we'll also take a look at some of the equipment being used. I'll also be providing some data sheets, Excel data sheets, so that you can perform like simple graph plotting and some simple understanding of how different curves come of different cell chemistries. So we'll also be taking a look at the cell data sheet, and also we'll take a look at what are the different testing standards, right? So there are many different testing standards as per, in different parts of this globe. We use different standards like ISO, UL, SAE, or Department of Energy. There are so many such standards. Yeah. So we'll take a look at basically some of them, and also we'll try to see some of the important understandings that we can obtain from cell testing. Okay. So with that, we will just take a brief look at today's agenda. So as I said, we'll start with introduction to cell testing and the need for cell testing. So what is the purpose? Why do we do cell testing? What is the importance? Then we'll go to cell data sheet reading. So basically, we'll just see a basic, just a basic and simple data sheet, cell data sheet. And finally, we'll also look at the cell testing standards, right? So as I had mentioned earlier, ISO, UL, and all of these. And then cell testing methods, so which we'll classify into 3. One is performance tests, one is physical abuse tests, and one is life cycle test. Yeah. So each of these will take a look at some of the examples, some of the example tests that will be performed or that will be categorized under these. Yeah. And then we'll take a look at the testing equipment, what we use here at Decibels Lab and also at some other companies across the globe. Yeah, like Tesla, Volvo, Scania, and all these. And then finally, we look at what is the final overview and what do we understand and what do we gain from cell testing. Yeah. And where will the obtained data be used further. Okay. So this is today's content. And without much delay, so let's begin with the introduction part. Okay. So let's try to first understand what exactly is cell testing, right? So in order to first and foremost get a good understanding, get a good hold of what cells do and how cells behave in real life, you have to first understand what situations they can encounter or what situations they will face or they're most likely to face in real life. Yeah. And here you can see below, these are the list of the such possible scenarios, starting with different ambient temperatures, which is probably the most obvious situation that this particular set of batteries or cells can face, right? So you'll say that you have an ambient temperature of say 25 degrees. Its behavior at this temperature would be totally different compared to how it would be performing at 0 degrees or even lower than 0. Yeah. And it would be very different from what it would behave at high temperatures, like 45 or 50, 55 degrees Celsius. So like basically to say it would perform vastly differently and would give you completely different behavior and cycle life, when you expose these cells and batteries to such varying temperatures. Yeah, so in order to understand this variation, this effect of varying temperatures on the cells, it has to be tested in these situations, right? So just like how we perform it in different ambient temperatures, we also perform it in different pressures. So that's basically called altitude test. So we'll classify this as altitude test. Okay, to see how the effect of pressure, how the effect of change of pressure will change also the behavior of the cells and on overall the battery itself, right? And similar to pressure, or which is interrelated to pressure, we also have humidity. So humidity is nothing but the water vapor content. Okay, so water vapor, or also this is called as dewing and condensation, which I'll come to later in just a while. We'll see that point later. And here we also have physical disturbance. So basically it's like suppose the battery gets impacted, or whether it experiences an accident, or a sudden drop, or a sudden change in g-force, or severe vibrations coming in from the vehicle or from the motor. Yeah, also temperature disturbance. So there's something called as thermal shock. So there's like rapidly changing temperatures. And also electrical malfunctions, things like short circuit, or extremely high rate of discharge, or extremely high rate of charging. So how exactly all these forms of disturbances can affect the battery? Yeah, so these are the different situations in terms of physical disturbance that the cell and the battery pack as a whole can face. Okay, so as I had mentioned, overcharging and over discharging, that comes under electrical abuse. Okay, uh, this comes under thermal abuse, thermal shocking and thermal shock cycling. They both come under thermal abuse, and vibration comes under mechanical abuse. Yeah, so these are the three different types of disturbances. And then we have dewing and condensation. So as I had mentioned, different humidity test. So along with water vapor test, we'll also have dewing and condensation test. Okay, and also another classification, which is called submersion test. Submersion test. So basically, the battery pack as a whole is taken and it is dipped into a water tank to see what exactly is the endurance of this particular battery pack. Will it survive? For how long it will survive? Will water affect the internal portions of the battery of the cell? Will it reduce will it reduce the performance, or will it alter the performance in any way? So similar to how we have water vapor test, we'll also have dewing and condensation, and also submersion test. So water submersion test. And then coming to extreme situations. Okay, so basically we know that battery packs do require protection systems, right, in like electric vehicles especially. So it's to like prevent any harmful operations from the battery pack. But in case they fail, which is also possible in real life operation, so in case they do fail, how or what exactly will be the aftermath, or how exactly the cell will behave, the battery packs will behave after the protection systems have failed, right? So that is all, that also has to be analyzed, and that is why all of these situations apply to this particular classification called cell testing. Yeah, so the cell is tested in all of these different situations, and along with overheating as well. So this is a part of thermal abuse, right? So these are all the different possible situations, or these are all the different possible scenarios that a cell, not only a cell but a battery pack as a whole, can face, right? And by subjecting these cells and this battery pack to these kind of conditions, these kind of scenarios, we can finally determine how exactly they can behave and how exactly they are affected in these different situations. Yeah, so this is basically what is simply we understand by cell testing. Yeah, so keeping these points in mind, we'll now look at the need for cell testing. Okay, so by performing cell testing, so by subjecting the cells to all of the previous situations, all of the previous conditions, we can first and foremost, which is the most important, understand the limits of operation, right? So we get to know what is the operating window or operating limit, what the upper and lower operating limit of the cell and the battery pack. So this limit could be in terms of voltage, current, state of charge, charging, discharging capacity, charging and discharging rate. Okay, so the rate at which they can be charged and discharged, whether it's fast, very fast rate, slow rate. Okay, the amount of energy utilized, the power consumed, right, the voltage window, and also varying atmospheric conditions. So all of these can pose as potential limits to the operation of the cells and the battery packs, and this is the limits that we can obtain by performing cell testing. So this is the most important, one of the most important points, right? So following which, we'll also be able to understand real life characteristics and also behavior of the cells at cell level, module level, and at pack level. So basically, a battery pack, it is not just a collection of individual cells. Basically, it is cells that is made into small groups called modules, and group of modules that form a battery pack. Okay, so that's how we classify battery packs. And by performing cell testing, we also know what are the real life characteristics, like its internal resistance, its voltage behavior, its current, its capacity, all of these. So the next point would be that we can analyze battery pack failure points. Okay, so the areas or at the situations where the battery pack is most likely to fail, and establish a design for failure accordingly. Okay, so not only in battery packs do you have design for failure, but also in mechanical systems, right? So if you're trying to build some sort of an automotive, some sort of chassis or a suspension system or anything as such, we also do something called as design for failure, right? So we try to analyze at what point they can possibly fail and design that particular structural component accordingly. So just like that, we also have the same concept for battery packs. So we can analyze, okay, at this extremely high rate of current, the battery pack is likely to fail, or at this high level of energy, the battery pack is likely to overheat. And with that understanding of failures or failure points, we can design for failure. Okay, this is called DFME, design for failure, DFMEA, right? Design for failure and design for prevention as well. So failure for design for prevention of failure. So accordingly, we can design safety algorithms. That's the next point. We can define and design safety devices, safety algorithms, and prevention circuits. Okay, so basically, we can introduce circuits and also battery management system at both the cell and the pack level. So all of this is necessary, and this is exactly what we can all understand by performing cell testing. Yeah. So the next point, we come to something called as cell aging. So basically, cells age upon repeated usage. So over time, you'll see that its ability to give the same amount of power or energy or voltage will not be the same as it was when it was brand new, right? So by performing this cell testing, we can analyze and predict basically at what point will the cell age, how long will the cell and the battery pack last, right? And we can derive important parameters such as state of health and life cycle performance. Okay, so with all of this, we'll also be able to understand at what point will the battery pack completely stop working, or at what point does the battery pack require replacement. Yeah, so all of this can be understood using cell testing as well. So we can get the cell aging. Then finally, which we had seen earlier, so physical damage, the effect of physical damage. So electrical abuse, mechanical abuse, and thermal abuse. So all of this put together can also be analyzed, and its effect on the performance of the cell and the battery pack as a whole can be understood. Yeah. So keeping all of these points in mind, finally, what we come to, so we can finally tweak the performance of the cell and the behavior of the cell to get maximum operational efficiency. Yeah. So we know, okay, we have performed cell testing, we have performed various different tests, we have collected a lot of data, we have understood so many different parameters. Finally, what do we finally arrive at? We finally arrive at tweaking the performance of the cell according to the need and the requirement. Okay. So these are all of the need for cell testing. And this is what we can conclude that this is why cell testing is required. Okay, so now that we have understood the need for cell testing, let's take a brief look at the cell data sheet, right, provided by the manufacturer, right? So here we can see, first and foremost, the term over here called nominal capacity, right? So what exactly does nominal capacity mean? So it is basically the rated capacity of the cell, the rated discharge capacity of the cell at a certain current rate at a certain temperature. Okay, so here you can see this is the rated temperature at 25 degrees Celsius, room temperature, and this is the standard current at which it has been discharged. Okay, so if you discharge this particular cell at 0.52 amps, okay, then it would give you a capacity nearly close to 2600 mAh. Okay, so that's what we understand by nominal capacity. It's what the manufacturer rates the capacity of the cell to be, right? So this is a tested value. So if the cell was to be discharged continuously at 0.52 amps, then they would attain a capacity close to 2600 mAh. Okay, so here you can see, similar to nominal capacity, there's a terminology here called nominal voltage. Okay, so nominal voltage is basically like it is the voltage exactly at 50% of the battery capacity. So exactly at 50% at the at the 50% window, what exactly is the voltage reading? That will be that'll be nothing but the nominal voltage. Or you can also say that it is the average voltage of the cell over its entire performance. Okay, so for example, I fully charge the cell and I start to discharge it all the way till its end voltage, and if you take the average of all of this voltage, then you get a nominal voltage of 3.7 volts. Okay, so either definition you can take. And then internal impedance, this is it's not a very important parameter to understand, but anyway, you just have to know that the internal impedance is the collective internal resistance which is provided by the cell, the resistance to current. Okay, so it's, in this case, it is rated to be less than 70 milliohms. And discharge cutoff voltage, so this is the lower voltage. Okay, so the lowest possible voltage that the cell can be taken to, and below which it will enter something called as deep discharge. It's not safe to take the battery or the cell below 3 volts. Yeah, and then similarly we also have maximum charge voltage, so 4.2 volts. And again, if you go above 4.2 volts, you would enter over voltage, right? So from these numbers, you can directly tell that this is a lithium ion cell because of its nominal voltage. And then you can see here standard charge current. So if you were to charge the cell with this kind of current, then you would get maximum charging efficiency. Okay, so what that means is your cell will not degrade quickly if you were to keep the charging current limited to whatever value has been specified here. So likewise, you can see for others as well. So rapid charging current and standard discharge current and rapid discharge current. So if you were to stick to these values, then your cell would give you maximum operational efficiency. Yeah, and there is one more value that you can see over here. This is called maximum pulse discharge current. So if you were to discharge the particular cell in pulses, okay, so instead of drawing continuous current like this is continuous current. So let's draw a graph here. So this is current versus time, and this will be in amps, right? So if I were to draw continuously, then this is what we have over here. This is the standard discharge current over here. Okay, so what does pulse discharge mean? So basically, pulse discharge is nothing but drawing the current in pulses. Okay, so it will not be continuous, it will just be intermittent like this. Okay, and that is what you see over here, right? So this is basically what is maximum pulse discharge current, and it can accept a maximum value of 2.6 amps. Okay, so these are the most important parameters to understand from a cell data sheet, and all of the cell testing has to take place within this limits that have been specified over here. Okay, so with that, we will proceed to the next one. So here also, before we proceed, also we can see here what is the operating temperature limits. So 0 to 45 degrees during charge and During discharge, it is minus 20 to 60 degrees Celsius. And this is common to almost all lithium ion cells. Okay, so yeah, now we come to what are the different cell testing methods or procedures that have to be performed in order to certify or in order to qualify a cell for roadworthiness. Okay, so now once we perform all of these tests, so whatever cell testing uh, procedures that you see here, so once all of these are performed and once all of these are certified, as in to say, if the battery pack and the cell has cleared these tests, then it undergoes something called as roadworthiness certification. Okay, so what that means, it is roadworthy. Roadworthiness. Okay, so all of this is needed in order to get the roadworthiness of the battery pack. Okay, so in the upcoming in this session, what we're going to see, we are going to see static capacity test at room temperature and at different ambient temperatures, also at different C rates. Okay, and then what we're going to see, we are also going to see pulse power characterization. Okay, so this is also abbreviated as HPPC. So hybrid pulse power characterization. So we will see these three tests in terms of performance, and in terms of abuse, we are going to see thermal shock cycling, vibration, and short circuit. So these three are the ones we are going to see in terms of abuse test, electrical and thermal abuse test, and mechanical abuse test. And then finally, in terms of life cycle aging, we are going to see cycle life and state of charge loss at storage. So what exactly that means is, if you were to store a cell for a very long time or a battery pack for a very long time, what is the amount of energy or capacity which will be permanently lost due to storage? So that is what we're going to see in this upcoming few slides. Okay, so this is the complete set of or complete range of tests that is usually performed in order to have roadworthiness acceptance. All right, so now we will start with performance tests. Okay, so we'll first start with static capacity test. And the first one we're going to see is static capacity test at different C rates. Okay, so here we will see, so this is the static capacity test at different C rates. Okay, so you can see now, the objective of this particular test is to understand and to derive what is the nominal capacity that the particular cell can give at room temperature. Okay, so this particular test is performed at, initially it will be performed at room temperature. Okay, so which is generally at around 25 degrees Celsius. Okay, so once we, so now we know the objective. It is basically to obtain this the discharge capacity of the cell. So we can perform this cell at different C rates. Okay, C rate is nothing but the magnitude of current being discharged from the cell, right? So it can range anywhere from 0.3 C all the way up till 2 C. Okay, so what happens is the cell is first allowed to soak at room temperature. So basically, soak means it's allowed to rest at room temperature. Okay, that's so that the cell achieves thermal equilibrium and chemical equilibrium, right? And then what happens is that particular cell is discharged at constant current. Okay, so the cell is discharged at constant current. Okay, so what that means is the value of current will be held constant, and the cell will be discharged all the way from its maximum rated voltage till its minimum rated voltage. Okay, so in this case here it will be 4.2, right? And the minimum voltage will be 2.85. Okay, so this is for a lithium ion cell which is of 2600 mAh nominal capacity, right? So this, and these are the curves, or this is the kind of curve, voltage curve you can expect once you perform the static capacity test. Okay, so what we'll do now is I will upload few Excel sheets so that you can all plot few of the graphs. Okay, so yeah, I will just okay. So first I will upload this file. So I hope that all of you have received this. Is static capacity test for an NMC cell, or basically NMC is uh, nickel manganese cobalt type cell. Okay, you can just download this file, right? And once you have downloaded this file, please open to a specific page. I will just let you know which page that is. So there are up to 14 different sheets. You can I have like I have uploaded the file. You can just download it directly to your desktop. Okay, so I hope now my screen is visible for this particular Excel sheet. Okay, so this is basically the tested data. So like I have uploaded the file for everyone. I hope that you have received it. It is there in the chat box. Please do check it out in the chat box. The file is available. It is called static capacity test NMC. Okay, so so now what we're going to do, so just to show you how the voltage curves would be for different C rates, I'm just going to just simply show you how exactly the graph would come like. Okay, so okay, yeah, I will upload the file. Okay, so I hope now people have received it. I have just sent the file. Yeah, please do download this file and open it directly in the. Okay, so here you can see the graph. Okay, so this is the kind of graph you can expect, and you can just change the x and y axis limits. You can just change this to 2.5. Okay, so yeah, this is the kind of graph that you will be expecting at 0.2C. Okay, so whatever graph you see here, this is basically the voltage versus discharge capacity. Okay, so whatever y values you see here, this will be voltage. Okay, and here this will be discharge capacity. Discharge capacity in amperes. All right, so this is the x and y. If you plot discharge capacity over here as the x-axis and voltage as the y-axis, then you can get this kind of a graph. Okay, you can please check in the chat box. It is available to everyone. So please do check. And once you do open the Excel file, please go to sheet number 8. And in sheet number 8, you will find two values here. One is called discharge capacity in amp hours, and one is called voltage in volts. And you can just plot this this particular graph uh, in Excel itself, right? So this is the kind of graph you can expect at point 2C. Okay, and you can also try and see what are the values you can get for different C rates as well. Okay, so this one at sheet 9, the next sheet, here you can just plot the same graph, and you will see that this will be having a slightly lower capacity compared to the one for point 2C here. Okay, so you can just change your x-axis limits, x and y-axis limits. Okay, so now if you compare the previous two graphs, the previous graph to this graph, so the graph which we saw at sheet 8 to the graph which we saw at sheet 9. Okay, so just by keeping the cursor here, you can see that the capacity is close to its nominal capacity at 2500 mAh almost, right? But you can see over here at 2390 mAh, this is at 2C. Okay, so if you discharge the cell at 2C, this is the kind of graph, or this is the kind of capacity. This is the discharge capacity you will obtain. Okay, so like that, you can actually plot the discharge capacity versus voltage for different C rates. Okay, so sheet 8 is at 0.2C, sheet 9 is at 2C, and then so on and so forth. You'll find it at different C rates. Okay, so the exact list of C rates you can see over here. So 0.3C onwards, so you'll see, so 2C, 0.6C, 0.9C, all the way up till 1.8C. Okay, so these are the different C rates at which this particular cell has been tested, and static capacity test has been performed. Okay, and you can see here that there is a significant difference between each of the voltage curves at each C rate. Okay, so the reason is because chemical reactions inside the cell don't have enough time to complete at higher currents, right? And since the reactions don't have enough time to complete, the ions don't get fully absorbed inside the electrodes. Okay, so because of that, there is something called as capacity fading. Okay, this insufficient time for the reaction to complete causes this capacity fade, and some amount of capacity will be lost at higher C rates as when you discharge the cell at high C rates. Okay, so this can actually affect the cell, and it can actually reduce the life cycle of the cell. Okay, so you can see this difference over here. Okay, so what you can see, the capacity discharge capacity of the cell when you discharge it at 0.3C, okay, versus what you will see, what you will observe when you discharge it at around 2C or even at 1.8C. Yeah, so basically this is the effect of discharging the cell at high C rates. Okay, and this difference that you see between capacity at high C rate versus low C rate, this difference is called capacity fading. Okay, and this increases the more you discharge the cell at high C rates. Okay, so that is why it is always preferred to keep the cell within 0.2C to 0.5C and not discharge it at very high C rates. Okay, so this is what we'll understand from static capacity test, right? So one of the objectives is that we can obtain the discharge capacity of the cell. Also, we can derive we can understand the capacity fading. So to what extent capacity is fading at higher C rates. Yeah, so that is what we can understand from the static capacity test. Yeah, so before we proceed, I can also provide another file over here. So that is for NMC. You can actually try that out as well. For LFP. So I have sent for NMC. You can also see for LFP, which is lithium iron phosphate. It is a slightly different chemistry compared to NMC chemistry. So I have uploaded that in the chat box now. You can just try and download it. It is called static capacity testing, LFP. Okay, and you can try to perform the same graphical analysis. You can just plot discharge capacity versus voltage, right? And you can just try to understand like what is the different sort of graph you can expect. So you can just quickly show that over here. Okay. Yeah. So this is for the LFP cell. I have uploaded it in the chat box. So has everyone received the file? I have uploaded in the chat box, static capacity testing. Okay. No worries. I will upload it again at the end of the session. Okay. So here I'll just plot it quickly for you all. So just another graph. So here you can see how this is like totally different from an MC chemistry. Okay. So okay. So here you can see. So your NMC cell came from 4.2 volts. It came down like this, right? But here you can see LFP cell has a completely flat profile. Yeah. So just like this, different types of chemistries and different types of cells with different capacities can be tested. Okay, and their actual capacity, or that the capacity they deliver in real life, can be estimated. Yeah. So if people have not received the file, it is okay. I will upload it once again at the end of the session. Please don't worry. And you can try and perform the same graphical analysis. So again, over here, you can see discharge capacity and voltage. So if you just select these two, and you can just plot the particular graph to understand what is the discharge profile. Okay. So yeah, and with this, we will proceed to the next topic. Okay. So now we have seen static capacity at different C rates. Okay, so that is nothing but at different current magnitudes. So now we'll see static capacity at different temperatures. Okay, so similar to how the C rate test was performed, here the current value that is being discharged from the cell will be kept constant, while the temperature will be varied. Okay, so the ambient temperature of the cell will be varied. You have so as per ISO standards, usually you will vary it from 40 degrees to negative 20 degrees Celsius. Okay, so taking the cell beyond 40 degrees is actually not safe. It is not recommended because the cell can potentially explode, or it can cause harmful reactions to occur within the cell, and it can cause some toxins to be released from within the cell. Yeah, some toxic gases or some toxic chemicals. So for that purpose, usually it is limited to around 40 degrees Celsius. Okay, so you can see here the effect of varying the ambient temperature on the discharge capacity of the cell. Okay, so here also it is performed on the same cell, on a 2600 mAh cell. Okay, so here you can see at ambient temperature of around 20 degrees Celsius, it is giving you very close to 2600 mAh, right? So this is the orange line. While if you increase the temperature, you can see that it's giving you almost like, you can say that it's giving you beyond 2600 mAh. So why is that the case? That is because at higher temperatures, your ions inside the cell, during the chemical reactions, the ions will have higher energy. Okay, so it will acquire a higher amount of energy, and it can overcome resistance easily. Okay, so whatever resistance is being offered, or whatever resistance is being given by the cell to the discharge current, that resistance will be overcome by the ions because of higher available energy. Yeah, so which is why at 40 degrees you will see that it gives its complete nominal capacity or slightly even higher. Okay, so while that is beneficial, it is not, I mean, it is not completely safe to do it always. what can happen is like at any point in time, if the reactions go out of balance, then immediately the temperature of the cell can suddenly rise and it can catch fire. Okay, that's what is called as thermal runaway. So which is why it is not safe to operate the cells at around 40 degrees Celsius or close to like 40, 45, even 50 degrees Celsius. Okay, so at this point in time, if there is sustained operations at this kind of temperatures, then a coolant or a coolant system has to be activated. Yeah. And now let's take a look at the performance of the cell at lower temperatures. So we saw at higher temperatures, it's not safe to do it, even though it does give you a good discharge capacity. At lower temperatures, what will happen? You can see over here, these two blue lines. Okay, so especially at -10, -15, -20 degrees Celsius, what's going to happen? Yeah, so your ions will lose energy. Okay, so your ions will lose energy, and during the redox reactions, your ions will not have sufficient energy to overcome internal resistance, right? And also what will happen? Your electrolyte, the cell's electrolyte, it will start to freeze. So because of which your ions will not freely flow between the anode and cathode, and that will cause a reduction in discharge capacity. So which is why you can see here, at even though it is 2600 mAh rated, you can see the capacity reduces drastically to about 1.5, right? So almost 50% of capacity is being lost here because of like reduction in ambient temperature. Yeah, so this is why again it is not safe to operate the cells over here. And what can happen here is not only capacity fading can occur, but the cell can get permanently damaged. Okay, so I mean that even if you like operate the cell at very low temperatures for even a small amount of time, it can permanently start to lose capacity pretty fast. So rapidly it will start to deteriorate. So it is important to bring in some sort of a heating system here, so that the cell is taken to like 20-25 degrees optimum operating temperature, and then you can like safely operate the cell. Yeah, so this is static capacity test at different ambient temperatures. Okay, so basically the objective of this test is to understand and determine what is the discharge capacity of the cell at different ambient temperatures. Okay, so how this test is performed, basically, so similar to how we kept the cell for C rate, the testing at different C rates. Similarly, even the test device will be a thermal chamber in which you'll basically lock the test piece, the cell test piece. You will lock it, and it will be airtight and watertight. Okay, so once the thermal equilibrium has been obtained, it will then start to discharge the cell at different C rates. So as and when the C rate, as and when the cell discharges to its minimum capacity, again it is charged and discharged at different temperatures. So like this, it will be repeatedly performed at different temperatures. Yeah. So that is basically testing the cell at different ambient temperatures. Okay, so now we will see here pulse power characterization. So this is one of the most important tests that has to be performed in order to characterize the cell. Okay, so basically characterization of the cell is nothing but determining its parameters, its most important parameters. So that is nothing but your internal resistance and capacitance of the cell. Okay, so that is why this particular test is performed, pulse power characterization. And basically this test is nothing but discharging the entire cell at pulses. So different pulses will be performed at different states of charges. Okay, so at different percentage of the battery. So we start at a fully charged battery at around 100%. Okay, we start the test at 100% capacity or at 100% state of charge. Then at intervals of 10% states of charges. So that means at 100%, at 90%, okay, and at 80%, so on till it reaches 0%. This particular set of pulses will be given. Okay, so you can see over here, these are all your discharge pulses. Okay, and at each discharge pulse, you will measure what is the internal resistance, what is the capacitance. Okay, and usually these pulses will be at 2C. Okay, so what that means is if the cell is rated at 2600 mAh, then 2C means a discharge current of 5.2 amps. Okay, so this is the standard rated as per ISO. So every time there's a pulse provided, it will be discharged at 2C and then charged again at 2C, and then finally it will be discharged every pulse. It will be discharged at 10%. Okay, so this is why pulse power characterization is performed. So at every pulse, you are able to measure the resistance, the internal resistance, and also the capacitance of the cell. Okay, so this is nothing but battery internal parameter estimation. Okay, that is why this particular test is done. It is done in order to accurately estimate the cell's resistances and capacitance. Okay, also it helps you to understand what is the dynamic performance characteristics of the cell over the entire capacity. Okay, so whatever capacity it has, so within that capacity, what is the capability of the cell and how well it performs within that capacity window. Okay, so similar, this is the current profile you see, and then here on the bottom right hand side you can see the voltage profile. Okay, so to each pulse you will be able to see a voltage profile over here, the voltage response. Okay, so what you see here is the response to individual, series of pulses. But if you want to understand what is exactly the response to one pulse, okay, so let's take one current pulse. So this is the current, and this is one discharge pulse that you see here. Okay, then its voltage will be recorded like this. Okay, so this is how its voltage will be recorded, and this is the voltage response of the cell. So for one discharge pulse, this is how the voltage response would look like. Okay, so in this voltage response, you will be able to estimate the internal resistance and the capacitance. Okay, so I will not go in depth into that, just because it's not part of the current scope, and also like it requires actual tested data, which currently I will not be able to provide for this. But this is how the voltage response would look like. And you can estimate the resistance by dividing this entire response into something called as steady state response. Steady state response, and also one more called transient response. Okay. Okay, so by analyzing these two responses, we'll be able to obtain the resistance and capacitance. Okay, so that is the importance of pulse power characterization. This is just one of the current pulses that that can be done. Like, but there are many more such pulses. There is another form in which like current will asymmetrically go on increasing and then asymmetrically go on decreasing. So the profile would look something like this. So if this is your zero line, okay, so it will start at 0 and then go like this. It will go on increasing like this, right? And then it will start to decrease once again. Okay, so this is one of the profiles that can be given in terms of pulse power characterization. There is also another pulse which can be given. Okay, so let me just extend this. Okay, so like another pulse which can be provided is basically let me just erase this part of, yeah. So here it can be given like this, just only discharges like this. No charging part, just only the discharging part. It will continuously go on increasing like this, and then it will end at one point. Okay, so there are different ways in which pulse power characterization profiles can be given. So this is also just one of them. Okay, so with this test, you're able to understand the internal parameters of the cell. Okay, so with that, we have finished the performance tests, and now we'll look into some abuse tests. Okay, so namely thermal shock cycling, vibration test, and short circuit test. Okay, so thermal shock cycling is nothing but subjecting the battery to rapidly changing ambient temperatures. So basically it starts at ambient temperature, say around 25 degrees Celsius. Okay, so it starts at ambient temperature, and then the battery pack is actually allowed to rest at 25 degrees Celsius till thermal equilibrium is obtained. Okay, so once equilibrium is obtained, it will then be the temperature will then start to change, and it will be dropped till minus 40 degrees Celsius. Okay, so once it is taken to minus 40 degrees Celsius, it will then be taken to plus 80 degrees Celsius. Okay, so this kind of change, rapid change from ambient temperature to minus 40 to plus 80 is called thermal shock. Okay, so basically it's nothing but rapidly changing ambient temperature, and this particular variation in temperature is done a minimum of 5 times. Okay, so this is called a thermal cycle. One thermal cycle is from minus 40 to plus 80 degrees, and this is repeated 5 times. Okay, and the objective is to understand what is the behavior and what is the response of the battery pack, what is the status of the battery pack in this entire thermal shock cycle that we perform over here. Okay, so at the end of this test, following things will be obtained. So basically, has the battery pack caught fire? Has it ignited? Okay, has it ignited? Has it lost any mass, or has it lost any material? So as in to say, is there any leakage of chemicals? Is there any gassing? So basically gassing is nothing but evaporation of the electrolyte. So usually in today's market, you will see that some of the electrolytes are organic in nature, and they start to evaporate, or they start to vaporize at very high temperatures. Yeah, and that vaporization is called gassing. So do any of these phenomenon, is any of this noticed? If any of these phenomenon is noticed, then the battery pack has failed. Okay, it has failed the certification test, or it has failed the acceptance test, and therefore it is no longer roadworthy. Okay, so if none of this is noticed, then it is roadworthy, and it will then be proceeded to the next test. Okay, so this is basically thermal shock cycling. And again, as I said, the goal of this shock cycling test is to subject a battery pack to such extremely varying temperatures, and to see whether any of these phenomenon occurs, like ignition or spontaneous combustion of the battery pack, any mass is lost, or any leakage, or any gassing. Okay, so these are all of the main parameters of thermal shock cycling. And this is usually done in order to understand how extreme temperatures will affect the battery pack in electric vehicles, especially on the road. Okay, and there is another name to this thermal shock cycling. It is also called thermal endurance test. Okay, so thermal endurance test. Okay, so that is with respect to thermal shock cycling. And now we have vibration test. Okay, so vibration test is where a battery pack will be kept on a vibration test bench like this. So what you're seeing here on the left hand side is the test bench, and it will be subject to vibration in all three directions. So in the x direction, that is the longitudinal direction over here, this is the x direction, right? Lateral direction y, and vertical direction z. So in all these three directions, it will be subject to vibration at 200 hertz. Okay, so this is specific to battery pack. It is not something that only one cell will undergo. The entire battery pack will undergo it, and it will be subject to minimum of 12 hours. Okay, so the reason is because the ISO standards detect that minimum of 12 hours is needed in order to sufficiently understand what is the effect of vibration on the chemicals present inside the cell, inside the battery pack. Okay, so again, same thing. If there is no venting, or if there is no leakage, if there is no gassing, if there is no leakage or any loss of chemicals, no loss in mass, no cracking, no denting, or no physical damage, or no explosion, if none of these are noticed, then again, the cell or the entire battery pack is roadworthy. Okay, so it will undergo this acceptance test. It is roadworthy. Okay, so this is with respect to the vibration test, and it is limited to 200 hertz because of the limitation due to the mass of the battery pack. So the battery pack is quite heavy when it is being like tested. So for that purpose, in order to prevent any damage from occurring to the machine also, it is limited to 200 hertz. Okay, so this is basically as per the ISO standards, and these are the ISO acceptance conditions. Okay, so this is with respect to vibration test. And then we come to the last part, which is short circuit test. Okay, so short circuit test is nothing but subjecting the cell to a scenario of short circuit, wherein the cell that you see here, this is just an example of a pouch cell. Okay, so a pouch cell which actually belongs to the EV itself, an electric vehicle. This pouch cell is connected to a wire with low resistance. Okay, so I will highlight the wire. So you see this wire, this thin wire over here. This thin wire is of low resistance. Okay, it is basically a low resistance of 0.1 ohms or lower than this. Okay, so this is again as per ISO standards. It has been over repeated testing. It has been seen that 0.1 ohms or lower will cause the cell to short circuit. Okay, so if you connect this low wire, low resistance wire to this particular cell terminal, then it is noticed that the cell will discharge a very high amount of current through this wire. Okay, so since the resistance is very low, the cell will discharge a very high amount of current, right? That's what short circuit means. It means nothing but a formation of a low resistance path. Okay, and that low resistance path can actually cause a high amount of current to be discharged from the cell. Okay, and this is a dangerous situation that can actually occur in electric vehicles when the battery pack is not insulated correctly. Okay, so basically this short circuit test is performed in this way, and the objective or the aim of this test is to see what is the functionality of the protective device within the cell. Okay, there are certain protective devices like current interruption device and circuit breakers, contact breakers. So to check how they function and also to see whether the cell will ignite. Basically, this is to see also whether the cell will catch fire. Okay, so even ignition is noted. Okay, at what current value or at what external resistance value will the particular cell catch fire. Okay, so repeatedly this particular cell will be subjected to the short circuit test until such time either it catches fire or till such time it passes the test successfully without any ignition. Okay, so this is the main criteria of the test. Okay, and all of these pouch types of cells will undergo external short circuit test like this. Okay, so it can be performed at different temperatures as well. So because as I had said earlier, the ambient temperature will also influence the chemical reaction occurring within the cell. Okay, so if the reaction rates were to occur at very high rates, then it is more likely that short circuit can occur much more easily, and it can also ignite much more easily. Yeah, so this is with respect to short circuit. Okay, so now we come to the last part, which is on aging test. Okay, so first and foremost, we'll look at state of charge or capacity loss due to extended storage. Okay, so again, as per ISO standards, the test device or the test piece is kept in a watertight and airtight storage unit at 45 degrees Celsius. Okay, as per the standards, and it is kept at a minimum of 50% capacity. Okay, so it has to be exactly at 50% capacity, and then it is left in that particular state, in that particular storage unit for a period of 30 days minimum. Okay, so after the 30 days is over, the device is removed or the test piece is removed, and then its capacity is checked again by performing a static capacity test. So if you remember, we had seen at the first what exactly is the static capacity test. So again at a constant C rate, so at 1 C rate it will be discharged, and its remaining capacity will be obtained by performing this particular test. Okay, so like this, the same test can then be repeated for an interval of 45 days, a period of 60 days, and then a period of 180 days, and then finally 360 days. So for one full year. Okay, so this is how this particular state of charge loss or capacity loss due to extended storage can be performed. Okay, so there are also other methods. It is not necessary that it is kept only at 45 degrees Celsius. Temperature can be changed, and it can be even kept at around 20 or 10 or 0 degrees Celsius, depending upon what is the requirement. Okay, so these are the different variations that can also be performed in SOC loss to determine the state of charge loss. Okay, so basically the test is to see how much of the capacity and how much of the performance is lost due to no usage. Okay, So now we come to the last topic, which is cycle life test. And this is to analyze how exactly the performance of the cell will start to deteriorate after continuous usage. Okay, so we had seen no usage in the previous topic, and in this topic we will see the deterioration of performance due to continuous usage. Okay, so basically what happens, you can better understand it through looking at a graph. Okay, so suppose this is the current profile that we'll provide. Okay, so this is the zero line. We'll charge the cell. Okay, so this is charging. So consider that positive side is charging and negative side is discharging, right? And we'll discharge it like this. Okay, so continuously this charge and discharge profile will be supplied. So up to more than 1,000 times. Okay, more than 1,000 times, more than 2,000 times, it will be continuously provided. Okay, and this is called basically charge and discharge cycling. Okay, so by performing or by subjecting the cell to this kind of a profile, what's going to happen is that the cell will start to lose its capacity, its charge and discharge capacity, its efficiency, and also its cycle life over time. Okay, so this is basically the discharge profile that will be supplied to the particular cell. Okay, and it is cycled basically between 80% charge and 30% charge. So continuously it will be cycled between this particular voltage window. It can also be varied. It needn't necessarily be kept between 80 to 30%. It can also be kept between 90 to 20. Okay, it can also be cycled between 60 to 40, depending again upon the requirements. Okay, so basically how it goes. So for in a day, in one day, for 22 hours, this particular profile will be provided. Then 2 hours it will be rested. Then again it will be for 22 hours of cycling, and then 2 hours of resting. So this will go on for 7 days. Okay, so this will go on for 7 days, and at the end of the seventh day, both a static capacity test and a pulse power test will be performed in order to see how much the resistance has changed, how much the capacity has changed, and how much the performance, the power and the energy of the cell has changed. Okay, so again the same thing will be repeated for 7 days, and at the end of 14 days the same test will be performed. Okay, so this will go on repeatedly till a minimum period of 9 months. Okay, so a minimum of 9 months is needed in order to achieve a total cycle number of 1,000 cycles. Okay, so this is continuous. So this will go on and on. It will take about almost 9 months to 10 months to reach a number of 1,000 cycles. Okay, so this is how cycle life test is performed. Okay, so again, this is purely dependent on what SOC or what percentage window you choose, and what number of life cycle targets you're willing to achieve. Okay, so depending upon that, your parameters will be changed. So whatever I have shown over here is as per ISO standards, and in that also they have shown they'll have mentioned exactly what are the different variations that can be performed in the testing parameters. Okay, so yeah, with that we come to the end of the different types of tests. Okay, and here at Decibels Lab, you can see this is the current testing equipment that we have. And as we speak right now, cycle test is ongoing. Okay, so what cycle test is ongoing, and right now we have completed 100 cycles so far. 100 cycles, and our future target is to see what would be the cell performance at around 500 cycles and then at 1,000 cycles. Yeah, so this is the equipment that we use, and the company is Niver. Okay, it is a Chinese brand which currently deals in battery testing and battery parameter estimation equipment, and it is an 8-channel battery system. So eight individual cells can be tested at one particular time. So you can see over here these are the different channels that we can see, and we have 2 devices, and currently right now one is working on cell cycling, so that is at cycle life and aging test. Yeah, so we'll also see how the interface of this looks like. So here is a test schedule. So simple for static capacity test, this is how you would provide it. So you'd provide this constant current command. Okay, so where the cell will be discharged constantly at this current rate. Okay, at 0.78 amps, it will be constantly discharged. Okay, so This is called as a test schedule, or also called as a step manager. Step manager. Okay, so you can actually you can provide the instructions as to what test has to be performed at what intervals and as such. Okay, so likewise, you can also see here for pulse power characterization, this is the kind of profile you perform. So at each step interval, so how much time should I provide the current for, and how much current I must provide till what limit, all that you can mention over here, the cutoff voltage, the discharge or charge current, what kind of step you want to perform, how much rest time you want in between each step, and how many times you want to repeat this entire test, from which step onwards, and when you want the cycling to end. All that can be provided over here. Okay, so this step manager can actually be like adjusted in all these ways. Yeah, and here you can see the testing facilities at Ather, at Tesla, and here you can see not only the testing benches over here. You can see that this is a similar equipment that's being used, and you can also see here the test chambers. Okay, so this is basically a temperature and humidity test chamber. So basically, like your cells and your battery pack as a whole will be like subjected to different temperatures, different ambient pressures, and also humidity, and its performance will just be analyzed using these test devices. Yeah, and Airbin over here, Tesla uses Airbin. So this is actually world famous, and there many organizations, many institutes use this for advanced cell and battery testing. And here you can see it also has a water submersion lab. So it's like it can actually like test different types of cells, like not only cylindrical cells but also like coin types, pouch type, uh, prismatic type, and all of those types of cells. Yeah, and then Sign Lab is global. Actually, it is not only for EV, but it's also for all other types of applications. Even Scania gives their testing from Arbin and Sign Lab. Scania, Volvo, Audi, Mercedes Benz, all of them majorly take their cell tests from Arbin and from Sign Lab. Yeah, so these are some of the testing facilities across the globe. So most commonly used ones. Yeah, and then finally we have the ISO different testing standards. So far we have seen mainly ISO. Yeah, but there is also IEC, which is actually meant for global applications. We have SAE. SAE is most commonly used in automotive applications. UL is also one of the major standards. It is not only used in automotive applications but also in household applications. And then you have US Department of Energy, which is specific to hybrid electric vehicles and also fully electric vehicles. And then you have ELICERT, which is also for automotive applications. Yeah, so all of these are the different ISO standards. All of these are the different testing standards, but we usually follow ISO standards. Okay, so with that we have come to end today's session, and then finally we can see the last bit of information. Just as an example, what ISO specifies should be the different currents and different temperatures for performing these tests. Okay, so at each of these C rates and each of these temperatures, the static capacity test must be performed. Okay, so thank you all. This is the end of our session for today. So yeah, now we can take some Q&A here. So if anybody has any questions, yeah, about regarding the file, no one has received it. No one was able to find the cells, the cell testing file that I had uploaded. Okay. Okay, just a moment. I will just try it once again. Let me just see if I can provide it to you. Okay. Can you please confirm now? if somebody has received it.
Yes,
Because
I can see in the chat box.
Yeah, in the chat box. So it is still not uploaded. Okay. Seems like people are not able to find it. Yes, I have sent it. Okay. This is a problem. Vinay, can you just try and send it just after some time? Meanwhile,
I'll do one thing. Yes, you can check back later, maybe after 8 p.m. or 9 p.m. In the course section. I'll get the file uploaded in the course section of our website.
Yes, Jagdish, I have sent it to everyone. There
yes.
seems to be a problem. I don't know what is the problem here.
Yeah, you can check back later in our website. In the course section, you can find it.
Yeah,
so arrange it for a file upload.
Yeah. So, like, if anyone has any questions, I'm free to ask. Feel free. So, any questions?
Yeah, I'll just share the certificate link shortly. Till then, if you have any questions, you can ask.
Okay.
I'll share it. Thank you, Binav, for the session.
Yeah, thank you, Vinayak, for hosting the session. I think that there are no questions, so I think